Good day, ladies and gentlemen. This is the 11th lecture in the second series of lectures related to the implementation of the RM software for filter design. In this lecture, we will talk about synthesis of selective band-stop active RC and SC filters and digital infinite impulse response filters. We'll be, as usual, naming the project, introducing the design requirement, synthesizing the transfer function, and then analysis of the results and synthesizing of the physical network. First, we will activate the main program and allow the blocked content and visit the recommended design sequence. In this case, we will enter the project name, then we will enter the design requirements, then we will go to the synthesis of a low-pass prototype, which in this case will be the elliptic filter, and after that finished, we will proceed to the program which performs transformation, which in this case will be low-pass to band-stop, and then we will proceed to synthesis. Now, let's start designing. The first action will be to introduce the project name, which will be band-stop elliptic. Now, since it is a band-stop, we go to the proper place in the interactive area. Here the quantities needed are explained, and we will supply them. First, we will enter the central frequency. The cutoff frequency of the upper passband will be, in this case, 105, which means we expect the suppressed or rejected frequency band to be about 10 kilohertz. The lower frequency of the upper transition band will be set to 101 kilohertz. Accordingly, we will give symmetrical data, so the cutoff frequency of the lower passband will be 95, and the upper frequency of the lower transition region will be 99 kilohertz. The input, the maximum passband attenuation will be set to 0.1 decibel, and the minimum stop band will be kept to 40. The minimum asymptotic slope will be set to 6 to allow full freedom. The group delay error is not of concern, and the normalization resistance will be 1 kilo ohm. So everything done, we may proceed to synthesis of a elliptic type 2 filter, and we will be asked for the order of the filter. Will you choose 6th order of the filter? So you probably notice we skipped the Zolotarev program, so that we practically are walking in the darkness by proposing this number, and then we will put two transmission zeros. The order of the numerator will be 4, and we may create the low-pass elliptic prototype. Since the process is iterative, we will pause the recording. The synthesis finished. We may now proceed with the next step, which is transformation. First, we should supply the type of transformation. In this case, that will be low pass to band stop, number 2, and run the program which performs transformation. You can see here it is a high pass band stop, and these are the zeros inserted at the central frequency. These are the transformed zeros, and it is specific here that the order of the numerator and the order of the denominator in this kind of filters is equal. Now we will go for the physical synthesis. First, the RC circuit in cascade. Done. Let's see what happened. First, we will look to the SPICE file. Here it is, and we will enlarge a little bit. Now we can discuss the subject of 0.1 decibels. It cannot be seen the variation of the passband attenuation, but we will enlarge that to see it again. What is the goal here is to see at which frequency is the 3 dB so it should be at 95, 3.439. The difference is at the bottom. Here it is, about that is the frequency of the, you see here, the frequency of the upper limit, and similarly here is on the other side is 105. And what is also of interest is this frequency, which was supposed to be 99, but it is much lower, which means that we could go with an order of the filter seriously lower, for example, 4th order of the filter. Now we will go for the schematic. And this is a 12th order filter altogether. So there are 6 second order cells in cascade. Now that being done, we will go to RC-parallel to see the parallel realization. Here is the SPICE file. Here it is. And now we may look for this variation in passband. As you can see, they are extremely small, 0.1 decibel, but still they exist. Okay, now let's go to the schematic of the parallel case. So 1, 2, 3, 4, 5, 6 cells in parallel, and the summing circuit and the details of the summation. Now we will proceed with the serialization, which first needs sampling frequency. We will use the same like earlier, and 1 picofarad as a normalization capacitance. This is the synthesizing program. Here is the SPICE file, and we will simply have a look at the SPICE file. For example, we will look to the first. We will it is half of the central frequency, which means it belongs to the passband, and we will look here to the output of the summing circuit, which is before the anti-aliasing filter. So and so on. That we lost. Here is the schematic. One, two, three, four, five, 6 parallel cells, and the summing, the anti-aliasing, sample and hold, and the system. And finally, we will go for the digital realization. And here is the CSV file, which will allow us to look to the frequency domain response of the digital filter. Of course, we will adjust a little bit the scale. We will start here with 60. And here we will reduce from 90,000 maybe 90,000 to 110,000. So this is the picture of the this is the phase characteristic, which is not telling very much. We will come to the group delay, but nevertheless, this is a unique capability of the RM software to extract the phase characteristic. And now we will go for the group delay. It should be a little bit better. And this is the group delay of this filter. So this ends the story about the synthesis of bandstop filter realized as active RC, active SC, and digital IIR filters. Thank you very much for your attention.